Hi everybody, I am Eurika. In many systems, such as the turbulent wake of a bluff body flow like shown here, we don't fully understand the principal mechanisms. In this video, I'm gonna talk about cluster-based reduced order modeling, or in short CROM, which identifies the principal mechanisms in an unsupervised manner directly from data. This method translates the nonlinear dynamics into a low-order linear model by assuming a probabilistic perspective of the system. In most real-world systems, such as the weather and climate system, the financial market, or the spread of disease, we don't know the governing equations. However, in fluids, we actually know that the flow is governed by the Navier-Stokes equations, which is the starting point for many model reduction techniques. One of the most prominent approaches for reduced order modeling are POD-Gayakin models. Here, the Navier-Stokes equations are projected onto a finite set of POD modes, yielding a nonlinear propagator with constant linear and quadratic term for the temporal expansion coefficients. This ODE describes how a single trajectory starting from an initial condition evolves in phase space. But researchers have also looked at the Navier-Stokes equation from a statistical point of view, with the aim to describe the evolution of the velocity field in terms of a probability distribution. This functional probability distribution would in principle contain all the information on the system that exists, all statistical properties and how they evolve in time. Hobbes' functional formalism is a famous example how to formulate a so-called Liouville equation for the velocity field. A solution to the Navier-Stokes equation can be seen as a point in the velocity space, like the phase plot in the left bottom corner. The Liouville equation describes then how a distribution of these points evolve over time. Then, given a particular phase distribution, the average of observables, such as the fluctuation energy, or a single component of the velocity can be computed. In general, these averages change in time. However, if the underlying phase distribution is stationary or invariant, the average will also be constant over time. Such a Liouville equation can also be formulated in the POD space as it is written here, which describes the evolution of an ensemble of trajectories governed by the POD-Gayakin model in phase space. But in contrast to the POD-Gayakin model, the Liouville equation is a linear partial differential equation for the probability distribution. It can be formally written in terms of the Perron-Frobenius operator, which maps an initial density forward in time. These two perspectives yield a complementary view on the system. Dynamical systems such as these POD-Gayakin models have a long tradition to be analyzed by geometric methods for global stability analysis or determining fixed points and limit cycles, finite time Lyapunov exponents, and invariant manifolds. On the other hand, invariant densities or distributions are fixed point solutions of the Liouville equation. Moreover, metastable and almost invariant sets can be determined. For instance, almost invariant sets are weakly connected regions in the phase space in which the trajectories reside for a long time. Let me emphasize again that by switching in the probability space, the governing equations become linear. This is not a result from any linearization, and this preserves the nonlinear phase dynamics. It is worth noting that the dual of the Perron-Frobenius operator is the Koopman operator, which acts on measurement functions in the phase space. These operators act on functions in phase space, providing a global description of the system. The Koopman operator has gained lots of traction over recent years for structure identification, reduced order modeling, and control. So check out Steve's video to learn more about it. The link is also in the description. Finding a linear representation for nonlinear systems can be extremely useful for control. There exist well-developed, powerful tools for state estimation, prediction, and optimal control for linear systems, which would become readily applicable for nonlinear systems. However, the linearity of the operators comes with a price. These are also infinitesimal, and it can be quite challenging to approximate them reasonably well. CROM represents such an approximation for the Perron-Frobenius operator that is learned directly from data and yields a very low-dimensional probabilistic model. CROM was inspired by works of John Burkhardt and his colleagues who used cluster analysis to find few representative states of a system that are used as a basis for a Gayakin model. And by Tobias Schneider and his colleagues' paper on transition matrix models to model the switching behavior between different coherent states in pipe flow. We combine these ideas to develop a low-dimensional probabilistic model that is estimated from data. In particular, this relies on a partitioning of the phase space into a discrete number of disjoint regions. Then the transitions between these regions are modeled as a Markov process, which is displayed here as a graph. The resulting model can be used to study the evolution of a probability vector, can be used to actually control the stationary distribution, and gives insights into the dynamical properties of the system. As this is a data-driven approach, the model can, of course, only be as good and as informative as provided by the data. Starting point of CROM is a time-resolved data sequence. In particular, we are looking here at a sequence of velocity snapshots as typically obtained from experiments using particle image velocimetry or from numerical simulations. The gray line represents the trajectory in phase space, and of course this space is much higher dimensional than shown here. We then partition the phase space using an unsupervised clustering algorithm such as k-means by grouping kinematically similar snapshots together. K-means aims to partition data into a discrete number of clusters, such that the similarity between observations belonging to the same cluster is maximized, while it is minimized for observations belonging to different clusters. The centroids of each cluster, here shown as black bullets, are the few representative states of the flow. These are computed as the mean of all observations in a cluster, naturally filtering out subscale structures. Finally, the transitions between those clusters are modeled as a Markov process. So the clusters are here for simplification shown as these boxes, and the transition probabilities are determined as relative frequencies of transitions that occur from one of those boxes to the other boxes over one time step. This approach frames high-dimensional nonlinear dynamics into low-dimensional linear dynamics in probability space, as represented by the Markov model, which can then be further analyzed. This approximates the probability distribution as a piecewise constant function on the set of clusters. Its evolution can be studied by powers of the transition matrix. For irreducible matrices, that means where all states are connected directly or indirectly in this transition matrix, any initial distribution converges to the unique stationary distribution after long times. This asymptotic state also corresponds to the dominant eigenvector of the transition matrix, with eigenvalue equal to 1, which is the only one that survives after long iterations and approximates the ergodic measure on the attractor. The second eigenvalue describes how quickly a distribution converges to the asymptotic state. The associated eigenvector is related to almost invariant sets, these weakly connected regions in phase space in which the trajectory resides for a long time before it switches between them. I recommend to check out Gary Froyland's tutorials and MATLAB code to learn more about this. A link is posted in the description. This approach is also closely related to Ulam's method for approximating the Perron-Frobenius operator. Ulam's method is a particular Gayakin method where the basis functions are characteristic functions based on a discretization, for instance, through a box covering like shown on this slide, of the phase space. By projecting the operator onto a finite set of test functions, the infinitesimal operator reduces to a Markov transition matrix. It was shown by Ulam for certain cases that the invariant distribution of the transition matrix converges weakly to the true one with finer and finer discretizations. Let's now dive into some examples. The first one is a two-dimensional simulation of a mixing layer flow. Two streams with different velocities create an unstable shear layer, which leads to the development of the Kelvin-Helmholtz instability and the roll-up of vortices further downstream. Occasional vortex pairing occurs, where two vortices start to rotate around each other and merge into a single one. A POD analysis can give some insights on the dominant structures and their dynamical behavior. On the left, you see the first 10 POD modes. The second mode, pair, represents vortex shedding, while the first mode, pair, is a subharmonic related to vortex pairing. The corresponding coefficients show that when the amplitude of the first mode pair decreases, that of the second mode pair increases, and vice versa. So the flow exhibits some kind of switching behavior. So we applied CROM to this data set, and this is the resulting graph extracted from the transition matrix and the centroids corresponding to each cluster. Safe loops in the graph, which occur because the trajectory spends some time in each cluster before it switches to another one, are neglected here. The clusters are sorted according to their dynamic evolution, which is depicted by the centroids. The clustering generalizes phase averaging, as can be seen from the centroid, which depict a certain phase of the flow. CROM identifies the two dynamical regimes corresponding to the two wave numbers and their intrinsic periodic behavior. Moreover, it identifies the bifurcation cluster in the center, which connects the two regimes. This can be seen as a precursor to the switching, which is important, for instance, for control if one wants to keep the flow in one of those regimes. As I mentioned, the evolution of the probability distribution on this set of clusters can be studied by powers of the transition matrix. For instance, entries of P with the power of 10 refer to the probability that the trajectory transitions from one cluster to another after 10 time steps. And please know that the transition matrix is here column stochastic. We can see that over time the probability diffuses. This is a result from the numerical diffusion introduced by the discretization. With increasing powers, all information on the initial conditions is eventually lost, and the system is on the attractor. The asymptotic distribution is shown in the bar plot in black. And white is the distribution of the data. So these distributions give you the relative frequencies or the average amount of time that the trajectory spends in any of those clusters. And the two distributions correspond quite well. The small distances are due to the fact that we have only 2000 snapshots to estimate the 10 times 10 entries of the transition matrix. We can measure the convergence behavior and also the length of the prediction horizon with entropic measures like the Kullback-Leibler entropy, which determines here the difference between the instantaneous transition matrix and the asymptotic one. The model has a well-defined prediction horizon, which is the time for the convergence to the asymptotic state. And it also incorporates transients in a robust manner. No matter in which cluster the initial condition starts, the model will finally converge to the attractor. We now look into one example on how to optimize the model to increase the prediction horizon. The model depends on several parameters: the length of the time series of the data, which we may not be able to change, the number of clusters, and the time step. The number of clusters determines how well certain phase space regions are resolved. Generally, one would want to resolve regions where rapid changes occur, like the bifurcation cluster of the mixing layer, better than regions with slow dynamics. But the goal here is also to obtain a low-dimensional model, which has a sufficiently high resolution to resolve the dynamics, but is low enough to understand the principal mechanism. A higher impact on the performance of the model has, in fact, the time step. A well-chosen time step for a given clustering can significantly increase the prediction horizon. So here I show you how to determine an optimal time step by minimizing the uncertainty in the model. This is based on comparing the trajectory of the data and that predicted by the model, which is computed as a spatial average using the probability distribution. Then we choose a time step that minimizes the error and maximizes the prediction horizon. Here the error is shown as a function of the time step. In the bottom you can see the resulting transition matrix, the eigenvalues of the model, and the evolution of two observables, the first and third POD coefficient. The red curve shows the evolution as predicted by the model, which quickly converges to 0. This means that the model in fact performs poorly. In contrast, the model corresponding to the optimized time step predicts the oscillations for quite some time. The decay of the amplitude is associated with the numerical diffusion introduced by the discretization, which acts here as noise. As you can see, optimizing the time step of the model has a huge impact on the performance. Let's move on to another more complex example, the turbulent wake of a bluff body, which exhibits broadband frequency characteristics. This is data from a three-dimensional large eddy simulation. So recently, Guillaume discovered that this flow exhibits bimodal behavior, so the switching between two states over long timescales. In the bottom, you can see the two symmetric vortices arising in the wake if averaged over time. In contrast, looking at instantaneous snapshots, one can see that the flow switches between two asymmetric states, where the vortex is dominant on one side of the body, while the vortex on the other side weakens. This behavior can also be observed in the evolution of the side force acting on the body. Extremal side force values correspond to these two asymmetric states in the wake. We applied CROM to this data set where we used 10 clusters. The plot shows the three forces acting on the body averaged over each cluster. There's not much variation for the drag and lift force over the clusters. However, the side force significantly changes depending on the cluster. Cluster groups can be defined by large positive, large negative, and vanishing side force values. The flow fields averaged over the observations of these three cluster groups exhibit the two asymmetric and the symmetric state. Obviously, these clusters can be associated with certain properties that may be desirable or not. For instance, strong side forces have a negative effect on the stability of a car. This is something we investigated more when using CROM for control. Check out my video on that. If it's available, a card will appear now. Let's look now at the dynamical model for this system. This is again a graph extracted from the transition matrix with the three flow states that I've just described. The model identifies the bimodal dynamics of the wake, the intrinsic oscillatory behavior, and the two branching clusters connecting those regimes. These cluster groups can be systematically identified by analyzing the spectral properties of the model. I'd like to point out that we did not impose any structure of the model or included any information on the physics of the flow. CROM extracts the principal mechanisms in an unsupervised manner directly from data, allowing one to identify different dynamical regimes and desirable and undesirable phase space regions. To summarize, I will give a brief overview of the main differences and similarities between CROM and POD Guillaume models, a standard technique for reduced order modeling. Both approaches start with an ensemble of snapshots that is first compressed into a few representative states of the system. For POD models, the velocity fluctuation is represented as a truncated series of POD modes, and one typically only keeps the high energy modes. In contrast, CROM relies on a partitioning of the phase space, and the representative states are the centroids associated with each region. Subscales are here filtered by averaging over each cluster. The model of CROM is a linear evolution equation for the probability distribution on the set of clusters. It describes how an ensemble, a distribution of trajectories, evolves over time. On the other side, a POD Guillaume model yields a nonlinear propagator for a single trajectory that can be further examined with respect to geometric properties in phase space, performing stability analysis, finding limit cycles and fixed points, etc. The probabilistic description through CROM enables one to determine sets in phase space with certain properties, like almost invariant sets and invariant measures, a robust approach to determine the long-time behavior of trajectories. Moreover, uncertainties are naturally incorporated by the size of the clusters. In contrast to the standard control and observer techniques that can be applied to POD Gayaki models, control design for CROM involves the control of an ensemble of trajectories. Check out the description to learn more about CROM and to get the code to try it out yourself. You will also find links to some of the references I mentioned. Thanks for watching.